A second sun hangs permanently above the horizon on a distant world. We are searching for planets where life as we know it could take root, and the results are astonishing. This journey will reveal 25 alien worlds with conditions that mirror our own Earth, from global oceans under dim red suns to super Earths with skies filled with multiple stars. You will discover which of these distant shores might already be home to another living civilization, and which hold the greatest promise for our future. We will explore why some of these seemingly perfect worlds may be treacherous traps, and why others, shrouded in mystery, could be the most likely to harbor life. What single quality do you believe is most essential for a world to become a home? Our stellar backyard holds a world almost within reach. Just over 4 light-years away, the planet Proxima Centauri b orbits the closest star to our own sun. This places it as our nearest known exoplanet neighbor, a rocky world tantalizingly close in cosmic terms. It resides in the habitable zone of its parent star, Proxima Centauri, a red dwarf far smaller and cooler than our sun. This means the planet receives just enough stellar energy for liquid water to potentially exist on its surface, the fundamental ingredient for life as we understand it. Yet this promising location comes with a profound challenge. The planet is almost certainly tidally locked to its star, much like our moon is locked to Earth. One side of the planet endures perpetual, scorching daylight, while the other is plunged into an eternal, frozen night. This creates a world of extremes, where the concept of a sunrise or sunset is unknown. But between these two harsh realms lies a narrow band of possibility, a place scientists call the Terminator Zone. Here, along the delicate line where day forever meets night, conditions could be just right. In this twilight ring, temperatures might be stable enough for liquid water to pool and flow. Imagine a landscape of constant, soft glow, with a star forever fixed on the horizon. Life, if it exists, would be confined to this ribbon of land, a world within a world. The very thought forces us to reconsider what a habitable planet truly looks like. Could an entire biosphere thrive in a single, slender strip of a planet? Yet this twilight world faces a peril far greater than its eternal day and night. Its sun, Proxima Centauri, is a tempestuous red dwarf prone to violent outbursts of energy. Imagine stellar flares of unimaginable ferocity erupting from the star and bathing the entire planet in intense radiation. These are not like the gentle solar flares from our own sun. A single one of these eruptions could deliver a lethal blast of X-rays and ultraviolet light, enough to scorch the surface and strip away the very air a planet breathes. Without a robust magnetic field or a thick, protective atmosphere, Proxima Centauri b could be a barren rock, its potential for life erased by the fury of its own star. This is the red dwarf challenge in its starkest form. A planet might orbit within the perfect zone for liquid water, but if its star is constantly trying to tear its atmosphere away, can life ever gain a foothold? The search for habitability becomes a search for planetary survival. Does this world possess a global magnetic field, like Earth's, that can deflect these stellar attacks? Could a deep global ocean or a dense, Venus-like atmosphere have shielded its surface? The answers will determine whether our closest exoplanet neighbor is a second home or a cosmic cautionary tale. The challenge of a solitary, storm-racked world gives way to an entirely different vision just 40 light-years away. Here, a single, faint star is orbited by a family of 7 known worlds, a miniature solar system packed into a space smaller than Mercury's orbit around our sun. At the heart of this cosmic commune is TRAPPIST-1e, a planet almost identical in size to our own. It sits squarely within the habitable zone of its ultra-cool dwarf star, a dim, long-lived beacon. From the surface of this world, The parent star would appear as a deep, crimson orb, large in the sky yet casting only a twilight glow. The other planets in the system would be impossible to miss, their orbits so close that neighboring worlds would loom in the heavens like our own moon, or even larger. You could watch their slow, stately dance across the sky, their surfaces perhaps showing clouds or vast geological features. This proximity raises a fascinating possibility. Liquid water could not only exist on TRAPPIST-1e, but across several of its sister worlds. This presents a concept that redefines the future of exploration, planetary hopscotch. Instead of a single, daunting voyage to one distant world, explorers could have a chain of waypoints. A mission could first land on an outer, icy planet to harvest water, then jump to a rocky neighbor to establish a base, with TRAPPIST-1e as the ultimate prize, a world with a climate that might feel almost familiar. The journey between these worlds would be a comparatively short leap, a matter of days rather than years, but such a crowded system comes with its own mysteries. With the planets gravitationally nudging each other, could their orbits remain stable over billions of years? And with their sun so dim, would they need thick atmospheres of greenhouse gases to stay warm? Or could a global ocean trap enough heat to create a worldwide temperate sea? This compact family of planets offers not just one candidate for life, but a whole menu of possibilities, all within a single stellar backyard. The discovery of Kepler-186f shifted our entire perspective on the search for other Earths. Before this world was confirmed, we knew of many giant planets, gas giants orbiting close to their stars. Kepler-186f proved that planets like ours, small and rocky, could exist in the precious habitable zone. Located about 500 light-years away, it circles a red dwarf star, spending its year within the region where temperatures could allow for liquid water. This was a monumental find. It told us that Earth-sized worlds in the right place are not rare flukes, but likely common throughout the galaxy, while its sun is smaller and redder than our own, casting a dim, ruddy light across the landscape. The planet itself is only about 10% larger than Earth. This small size strongly suggests a rocky composition, a solid surface where oceans could pool and continents could rise. What would it be like to stand on that surface? The sunlight would be more like our evening twilight, even at its brightest, with everything bathed in a perpetual, deep orange glow. The discovery of Kepler-186f opened a floodgate. It taught us to look for a different kind of habitable world, one that doesn't orbit a star like our sun, but instead thrives under the gentle, if faint, warmth of a red dwarf. This single planet expanded the cosmic real estate for life, proving that our pale blue dot is just one of many possible templates for a living world. While Kepler-186f revealed that Earth-sized worlds are common, another discovery presented a world that feels hauntingly familiar. Kepler-452b orbits a star that is a virtual twin of our own sun, a yellow dwarf shining with the same warmth and light. This planet spends its 385-day year within the habitable zone, a rhythm of seasons and sunlight that echoes our own. It is often called Earth's cousin, and for good reason. Imagine a side-by-side view of these two worlds. Kepler-452b is about 60% larger, placing it in a category known as a super-Earth. Its star, however, is 1.5 billion years older than our sun. This single fact opens a door to profound speculation. If life did arise on this world, it has had an extra 1.5 billion years to evolve. What might life look like with such a colossal head start? On Earth, that span of time covers the entire journey from the first single-celled organisms to the complex life we see today. A civilization on Kepler-452b could be immeasurably ancient, its technologies and societies beyond our comprehension. The planet itself might be a more mature version of Earth, perhaps with a thicker atmosphere or vast, continent-spanning forests. The silence from that region of space is not an absence of life, but perhaps a sign of a civilization that has long since mastered its environment, living in a harmony we can only dream of. This world challenges us not just with the question of whether life exists, but what life becomes given the gift of deep, cosmic time. A world of profound stillness might await at LHS 1140b. This super-Earth circles a quiet red dwarf star about 40 light-years away, and its defining feature is not what we see, but what we infer. Astronomers have measured its mass and size, and the numbers reveal an astonishing density. This world is heavy for its stature, a clear sign of a composition rich in iron and other metals, likely harboring a massive metallic core. Such a dense, rocky planet is a prime candidate for something essential for a stable climate, a global magnetic field. This invisible shield could protect the planet from its star's radiation, deflecting charged particles that would otherwise strip away a life-giving atmosphere. But the most captivating possibility lies in what that density implies for its surface. The planet's composition and position in the habitable zone point toward a world that could be almost entirely covered by a single, immense ocean. Picture an aquatic abyss of unimaginable scale, with no continents breaking its surface. The water could be dozens of miles deep, a global sea where the only land is the icy floor at the very bottom, under crushing pressures. In the perpetual twilight of this red, sunlit ocean, life would not be confined to a narrow strip, but could flourish throughout the watery depths. Bioluminescent creatures might illuminate the darkness, and entire ecosystems could thrive around hydrothermal vents on the ocean floor, drawing energy from the planet's warm interior rather than the dim light from above. This is not a world of coastlines and mountains, but a single, unified marine universe, a water world holding its secrets beneath a seemingly endless, placid surface. A mere 12 light-years from Earth, an ancient star holds a secret. Tidal star is one of the oldest red dwarfs we know, a stellar senior that has been burning for at least 8 billion years. This means its planets have existed for far longer than our own solar system. Orbiting this venerable sun is Tidal star B, a world that scores remarkably high on the Earth Similarity Index. This index measures how closely a planet's conditions, like its size and the energy it receives from its star, match those of our own world. By this metric, it is one of the most Earth-like worlds we have yet discovered. But its true significance lies not just in its similarity, but in its staggering age. Any life that might have arisen on this planet has had not just millions, but billions of years more to develop and complexify than life on Earth. Our entire evolutionary history, from the first microbe to modern humanity, has unfolded in just over 4 billion years. What could possibly emerge given twice that time? Imagine a biosphere where evolution has been running uninterrupted since our planet was a molten ball of rock. The potential for intelligence, for technology, for forms of life we cannot even conceive is almost limitless. This world forces us to confront a humbling thought. We may not be the pioneers of the galaxy, but the latecomers, looking upon civilizations whose history stretches back to the dawn of the cosmos itself. A world's fate can be decided by the temperament of its sun. While many red dwarfs are prone to stellar tantrums, the planet Ross 128b orbits a star of remarkable serenity. This quiet red dwarf, just 11 light-years away, emits very few of the violent flares that plague systems like Proxima Centauri. This calm, stellar nature makes its orbiting world one of our most promising targets for life. Ross 128b is a super-Earth, slightly larger than our own planet, and it rests comfortably within the habitable zone, but its true advantage is stability. Without constant blasts of radiation and stellar wind, Ross 128b has a far greater chance of holding onto a thick, protective atmosphere. An atmosphere is more than just air to breathe. It is a planet's blanket and its shield. It regulates temperature, distributes heat from the day side to the night side, and protects the surface from harmful cosmic rays. On a calm world like this, liquid water could persist on the surface, not hidden away in subsurface oceans or confined to narrow twilight bands. Imagine a landscape under a soft, perpetual red glow, where weather patterns could develop over vast continents and deep oceans, uninterrupted for billions of years. This stability offers life the one thing it needs most: time to begin, time to evolve, and time to complexify without the constant threat of stellar sterilization. In the search for a true Earth analog, a gentle star may be a more critical factor than a perfect orbit. Ross 128b stands as a testament to that possibility, a world where the silence of the heavens might be a sign of a vibrant, living world below. The promise of a calm world is matched by the sheer scale of another, GJ 357d. This super-Earth, discovered using data from the TESS Space Telescope, reveals how a planet can be both alien and profoundly familiar. Nestled in the habitable zone of its small, cool star, it receives a similar amount of stellar energy as Mars does from our Sun. This might sound cold, but for a planet with a sufficiently dense atmosphere, that energy is enough to create a global greenhouse effect, warming the surface to the point where vast, globe-spanning oceans could remain liquid. This is a world that is larger and more massive than our own, a true super-Earth. Its greater gravity would sculpt a dramatic landscape, with mountains potentially rising to incredible heights and canyons plunging to impossible depths. The sheer weight of its atmosphere would create a thick, insulating blanket, trapping heat and distributing it around the planet. The most compelling possibility is that GJ357d is not a rocky world with scattered seas, but a true water world, a globe completely enveloped by a single, deep ocean. Imagine sailing across a sea with no end, where the only land lies at the very bottom, under miles of dark, pressurized water. Life in such an environment would be entirely aquatic, perhaps building vast, floating ecosystems or thriving in the abyssal plains, completely isolated from the starry sky above. The discovery of this world proves that the habitable zone is not a one-size-fits-all concept. A planet that receives only a faint whisper of light from its sun can, with the right conditions, become a warm, watery cradle for life. The search for life took a revolutionary turn with the discovery of K218b. Here, for the first time, astronomers confirmed the presence of water vapor in the atmosphere of a planet orbiting within the habitable zone of a distant star. This is not just another world. It is a new category of possibility known as a Hycean world. Imagine a planet significantly larger than Earth, but not a solid rock. Its surface is almost certainly a single, globe-spanning ocean, dozens of times deeper than our own Mariana Trench. This immense sea is not capped by a nitrogen and oxygen sky like ours, but is enveloped in a thick, hydrogen-rich atmosphere, a vast, warm blanket of gas. This combination of a huge ocean and a hydrogen atmosphere creates an environment unlike anything in our solar system, yet one that could be a perfect crucible for life. The term Hycean itself combines hydrogen and ocean, perfectly capturing the essence of this alien world. The discovery of water vapor in its skies is the critical clue. It tells us that beneath that thick atmospheric shroud, a liquid water ocean exists, heated not by a nearby sun, but by internal processes and the insulating effect of its own atmosphere. This redefines the very meaning of a habitable environment. We are no longer looking only for pale blue dots like Earth, but for dark, deep ocean worlds shrouded in pinkish haze, where life could flourish entirely divorced from sunlight, thriving in the eternal darkness of the abyss. Could the first signs of life beyond Earth come not from a familiar continent, but from the steamy atmosphere of a planet-wide sea? The silence of a calm red dwarf is broken by another Earth-sized world, TOI 700d. Discovered by the TESS telescope, this planet is a rarity, a world almost exactly the same size as our own, orbiting squarely within its star's habitable zone. It is a place where the fundamental ingredients for life could align. Like many worlds circling these long-lived stars, TOI 700d is almost certainly tidally locked. One hemisphere is a permanent landscape of daylight, the other a frozen realm of endless night. The true potential for life here hinges on a single critical factor: its atmosphere. A thick, global atmosphere could act as a planetary life support system, circulating warmth from the scorching day side to the frigid night side. This would create a vast, temperate band where conditions remain stable, and liquid water could pool on the surface. Without this atmospheric blanket, the planet would be a world of unbearable extremes. This is why TOI 700d has become a prime target for the James Webb Space Telescope. Its powerful instruments are designed to do what was once impossible: to analyze the light filtering through this distant world's air. Scientists will search for the chemical fingerprints of gases like carbon dioxide, methane, and even oxygen. Finding them would not prove life exists, but it would reveal that this alien world possesses an environment that is not only habitable, but perhaps even inhabited. The secrets of TOI 700d are written in the faint starlight that passes through its skies, a message we are finally learning how to read. Some stars offer not just one, but two chances for life. Orbiting the ancient star Kepler-62, over 1,000 light-years away, are two worlds that seem to be made almost entirely of water: Kepler-62e and its sibling, Kepler-62f, are both super-Earths, larger and more massive than our own planet. Their size and density measurements point to a stunning conclusion. These are not rocky worlds with scattered seas, but likely water worlds, each enveloped by a single, globe-spanning ocean that could be dozens of miles deep. Picture an endless, unbroken expanse of water under a hazy sky, with no continents, no islands, and no shorelines in sight. The only land would be a layer of exotic, high-pressure ice at the very bottom, a floor to an aquatic universe. On such a world, the very concept of land is alien. Life, if it exists, would be entirely aquatic, forever suspended in a vast, three-dimensional marine habitat. Entire ecosystems could flourish at different depths, from sunlit surface waters teeming with alien plankton to the pitch-black abyss, where creatures might draw energy from thermal vents on the ocean floor. These two worlds, orbiting the same gentle star, present a profound vision of life's potential. It is a vision where biology has conquered an entire planet not by spreading across continents, but by filling an ocean from the top of its atmosphere to the very bottom of its sea. The TRAPPIST-1 system's wonders do not end with a single world. Beyond Planet E, three more siblings, designated F, G, and H, complete a stunning celestial lineup of potentially habitable planets. All orbit within or brush the edges of their star's temperate zone, creating an unprecedented laboratory for comparative planetology. Planet F is a cool, watery candidate, receiving a similar amount of stellar energy as Mars does in our own system. Its colder position suggests it could be a snowball world, or, if it possesses a thick atmosphere rich in greenhouse gases, a globe of liquid water. The next world out, Planet G, is the system's largest and a prime super-Earth. It basks in a gentler warmth, sitting comfortably in the habitable zone where its stronger gravity could easily hold onto a life-sustaining atmosphere. Finally, on the system's outer frontier, Planet H marks the boundary. This distant, likely frozen world may still harbor vast subsurface oceans, It's liquid water hidden deep beneath a thick crust of ice, warmed by the planet's own internal heat. The true marvel of this system is the opportunity it presents. For the first time, we can study 7 Earth-sized worlds around the same star, all at once. We can ask why one might be a barren rock while another is a water world, or why one developed a thick atmosphere while another lost it. This compact family offers a controlled experiment on a cosmic scale, a chance to understand the subtle recipes that turn a simple planet into a living world. HA 40307 G offers a refreshing departure from the stormy red dwarf worlds. This super-Earth orbits a star much like our own Sun, a stable, mature star that provides a familiar rhythm of light and warmth. Its year is longer than ours, about 200 days, placing it squarely within the star's habitable zone, where temperatures could allow for liquid water. But its most significant feature might be its orbit. Unlike the planets trapped in eternal embraces with their dim red suns, HD 40307G is far enough from its star to spin freely. This means it could have a normal day and night cycle, with a sun that rises and sets on a regular schedule. Imagine the profound implications. This world could experience seasons, weather patterns driven by the daily heating and cooling of its surface, and continents that are not perpetually scorched or frozen. The potential for a robust atmosphere is high, as the star's gentle nature and the planet's own stronger gravity would help it hold onto a thick blanket of air. This combination of factors, a sun-like star, a stable orbit, and the possibility of a temperate climate, makes HD 40307G one of the most compelling candidates for a world that feels like home. It is a reminder that while red dwarfs are common, the most familiar habitats for life might still orbit stars that remind us of our own. A mere 14 light-years from our solar system, a world of dramatic change swings around a quiet red dwarf. Wolf 1061c is one of our closest known exoplanet neighbors, a super-Earth with a mass several times that of our own world. Its proximity makes it a tantalizing target for study, a nearby laboratory for understanding planetary extremes. But this world's orbit is not a perfect circle. It follows a noticeably eccentric path, a stretched-out ellipse around its star. This single fact transforms its potential for life into a story of survival. Imagine a year on this world, a cycle of radical climatic swings. At its closest approach to the star, the planet is bombarded with intense heat, a scorching summer that could boil away surface water. Then, as it swings to the far point of its orbit, it enters a deep, long winter, a freeze that could lock the planet in ice. The entire world would experience a violent pendulum swing between these two states. For any potential biosphere, this is the ultimate test of resilience. Life would need to adapt not just to a single climate, but to 2 different worlds that alternate with the passing of each year. Could a thick atmosphere smooth out these temperature variations, distributing the star's heat more evenly across the seasons? Or would life be forced into a hibernating state, flourishing only during the brief, temperate periods between the brutal extremes? Wolf 1061c presents a powerful lesson. Habitability is not just about a planet's average temperature, but about its ability to maintain stability through the relentless cycles of its orbit. The sky itself becomes a spectacle on GJ 667cc. This super-Earth orbits within a triple star system, a celestial dance of 3 suns. From the planet's surface, the primary star would appear as a large, dim, red orb, while the 2 other, more distant suns would shine in the sky like a pair of incredibly brilliant stars, casting distinct shadows and bathing the landscape in an ever-changing tapestry of light. Despite this complex stellar environment, the planet holds a position of remarkable stability. It resides in what astronomers call the conservative habitable zone, a region where a planet with an Earth-like atmosphere could confidently maintain liquid water on its surface. This makes GJ667cc a particularly strong contender for habitability. The presence of multiple stars does not necessarily spell chaos. It can create a balanced gravitational symphony. The planet's orbit around its primary star is secure, while the other two stars circle each other far enough away to not disrupt its climate. Imagine a world where the sunsets paint the sky in triple hues, and the days are lit by a soft, crimson glow punctuated by the piercing light of its stellar companions. This planet proves that even in the most seemingly crowded stellar neighborhoods, a quiet, stable pocket can exist, a world where the fundamentals for life could assemble under a sky filled with suns. Sometimes the most profound discoveries are hidden in plain sight. Kepler 1649c was found not during the initial search, but years later, when scientists re-examined old data from the Kepler Space Telescope and spotted a signal that automated algorithms had mistakenly dismissed. This world, nearly identical in size to our own and receiving about 75% of the stellar energy that Earth gets from the Sun, is one of the most Earth-like planets we have ever found. It orbits a quiet red dwarf star, comfortably within the region where liquid water could exist. The combination of its Earth-like proportions and its gentle stellar energy intake makes it a standout candidate for habitability. From its surface, the star would appear large and deep red, casting a perpetual, warm twilight across the landscape. The planet's orbit suggests a year of just 19.5 Earth days, a rapid journey around its dim sun. But its true potential lies in the stability of its environment. Unlike many red dwarf worlds with chaotic orbits, Kepler 1649c follows a nearly circular path. This orbital stability is a gift, promising a climate free from the wild temperature swings that could freeze or boil a world's oceans. It offers the possibility of a consistent, temperate environment where life could take root and endure. This rediscovered world serves as a powerful reminder that our search for other Earths is far from complete, and that the answer to one of our greatest questions might be waiting patiently in data we have already collected. The recipe for a stable world might require an older, more patient sun. Orbiting the orange K-type star, HE 85512, is a super-Earth that has enjoyed a calmer stellar environment for billions of years longer than our own solar system. This class of star, slightly cooler and smaller than the Sun, offers a golden mean for habitability. They are far less prone to the violent flares of red dwarfs, yet they burn for tens of billions of years, providing a steady, unwavering light. Planet HE 85512b sits right on the inner edge of its star's habitable zone, a location that would typically spell a runaway greenhouse effect. But this world holds a secret weapon, one we are intimately familiar with on Earth: clouds. Sophisticated climate models reveal a startling possibility. If this super-Earth is covered by at least 50% cloud cover, those brilliant white swirls would reflect just enough of the star's heat back into space to prevent the surface from overheating. The clouds would act as a planetary thermostat, creating a global temperature that could average a pleasant 25 degrees Celsius. Imagine a world with a permanent, hazy sky, its orange sun softened by a luminous veil. Under that filtered light, vast oceans could sparkle, and continents could host temperate forests. This single calculation transforms our understanding of climate. It suggests that a planet's albedo, its reflectivity, is as critical as its distance from its star. A world that seems too hot at first glance might, with the right atmospheric makeup, be a paradise waiting in the shadows. A mere 12 light-years away, a star almost identical to our own sun holds a world of stark duality. Tau Ceti orbits a stellar twin, a star so similar to ours that it is visible to the naked eye in our night sky. This proximity and familiarity make its planetary system a prime target in our search, yet the planet itself presents a profound riddle. It exists right on the inner edge of its star's habitable zone, a precarious position that leaves its fate hanging in the balance. One path leads to a super Venus scenario, a cautionary tale of a climate gone horribly wrong. With a thick atmosphere dominated by carbon dioxide, a runaway greenhouse effect could have taken hold long ago. The planet's surface would be a scorching wasteland, with temperatures soaring to hundreds of degrees, hot enough to melt lead. Any ancient oceans would have long since boiled away into the dense, toxic skies, leaving behind a dry, hellish landscape under a perpetual, suffocating haze. This is a vision of a planet that had the potential for life, but crossed a climatic tipping point from which there was no return. Yet another, more hopeful possibility remains. If Tau Ceti possesses a more balanced atmospheric composition, perhaps with reflective cloud cover and the right mix of gases, it could be a super-Earth. Its stronger gravity could hold onto a life-giving atmosphere without triggering a runaway effect. In this scenario, the world might be a warm, water-rich planet, with global oceans and continents washed by humid air. The sunlight from its familiar star would feel warm on the skin, and the climate, while likely hotter than Earth's, could be stable enough for biology to flourish. The key lies in its atmosphere, a shroud that either traps fatal heat or regulates a global cradle. Is this nearby world a scorched relic of a failed climate, or a vibrant ocean planet awaiting discovery? Its silent presence so close to us serves as a powerful reminder of the delicate balance that makes a world a home. The discovery of GJ 581G revealed a world born not just from starlight, but from scientific conflict. Announced with great excitement, it was hailed as the first potentially rocky exoplanet found squarely in its star's habitable zone, a true Earth-like cousin just 20 light-years away. The data suggested a world with a stable, circular orbit, forever positioned in that Goldilocks region where water could flow freely. For a moment, we had our answer, a nearby shore that might harbor life. But then, other astronomers looked at the same data from the star GJ 581, and they saw a different story. The subtle tugs on the star, the very wobbles used to detect the planet, could potentially be explained by other factors, like the star's own magnetic activity and sunspot cycles. The signal for GJ 581G was faint, buried in the noise, and some teams could not find it again in their analyses. So, does this world exist? The question remains open, a subject of intense debate. This is not a failure of science, but its very heart in action. The process of discovery in exoplanetology is a meticulous dance of claim and counterclaim, of pushing data to its limits, and then subjecting it to the harsh, critical light of peer review. GJ 581G, whether it is ultimately confirmed or dismissed, taught us a vital lesson about patience and precision. It reminds us that every new world we find is a hypothesis, a whisper from the cosmos that we must strain to hear, and then work tirelessly to understand. Kepler 22b was the promise made real. Before its discovery, the habitable zone was a theoretical concept, a hopeful circle drawn around distant stars. This world, orbiting a star very much like our own sun, transformed that line on a chart into a tangible place. It was one of the Kepler telescope's first and most profound finds, a super-Earth circling squarely within that Goldilocks region where a planet's surface could be kissed by liquid water. Its sheer size, over twice the radius of Earth, presented an immediate mystery. Was this a massive rocky world, a super-Earth with continents of unimaginable scale? Or was it a mini-Neptune, a world with a small, solid core smothered under a deep, gaseous envelope thousands of miles thick? The answer lies in the nature of its embrace. If Kepler 22b is a rocky behemoth, its surface gravity would be intense, perhaps 2 or 3 times stronger than what we experience. Mountains would be lower and wider, and any life would be built for a world of crushing weight. But the more tantalizing possibility is that of a global ocean. A world of its size and composition could easily be a water world, a sphere shrouded in a thick, steamy atmosphere, with a single, endless sea covering its entire surface. The discovery of Kepler-22b did more than just add another planet to our catalogs. It ignited the public imagination. Here was a world with a 290-day year, orbiting a sun-like star, a place that felt both alien and strangely familiar. It was a headline that captured the world, proving that the search for other Earths was not just a scientific pursuit, but a human one, a quest to find our place in a galaxy that might be filled with warm, watery worlds just waiting for a closer look. Beyond our nearest alien shore lies a far more distant and frozen sibling. Proxima Centauri c orbits the same turbulent red dwarf as its famous neighbor, but it follows a path that takes it far beyond the warmth of the habitable zone. This world is a colossal super-Earth, a giant of rock and ice so distant from its dim sun that its surface temperature plunges to a lethal 230 degrees below zero. Any atmosphere would be frozen solid, lying on the ground like a blanket of snow, and water would exist only as ancient, cratered ice. At first glance, this is a dead world, a frozen monument at the edge of its star's influence. Yet, its immense size and distant orbit spark a different kind of speculation. A planet this large almost certainly possesses a family of moons, and it is on these hidden, circling worlds that a flicker of possibility remains. Imagine a moon not unlike Jupiter's Europa, locked in a gravitational embrace with this frozen giant. The relentless tug of war, the tidal forces, would squeeze and flex the moon's interior. This constant kneading could generate enough internal heat to melt subsurface water, creating a vast, dark ocean trapped between an icy crust and a rocky core. In that sunless sea, warmed from within rather than from without, the chemistry of life could still find a way. Proxima Centauri c itself may be a silent sentinel in the eternal cold, but its moons could be secret oases, their existence a testament to the fact that life's potential is not always written on the surface of a planet, but sometimes hidden in the dark, warm hearts of its orbiting companions. Titan star B offers a final, compelling argument for life's cosmic potential. Orbiting a quiet red dwarf just over 12 light-years away, this super-Earth is more than just another entry on a list. It represents a convergence of nearly all the favorable conditions we have encountered on this journey. Its star is one of the most placid known, a stable beacon that has likely not erupted in violent flares for billions of years, granting its planetary companion the gift of uninterrupted calm. This world rests firmly in the heart of the habitable zone, receiving a gentle warmth that could maintain liquid water on its surface, but its most telling quality is its remarkable score on the Earth Similarity Index, a metric that places it among the very top contenders for a world that feels like home. This is not a planet of wild extremes or chaotic orbits. It is a world of profound stability, where the forces that nurture life have been allowed to operate in peace for eons. The very air you might breathe could be rich and thick, held close by the planet's stronger gravity, creating a temperate climate across vast continents, or perhaps a single, globe-spanning ocean. Standing on its surface, you would look up at a deep red sun, fixed in a sky that has witnessed an unimaginable stretch of quiet history. As the final stop on our tour of 25 alien worlds, Titan's star B brings our search full circle. It reminds us that the galaxy is not just filled with bizarre and hostile environments, but also with serene, stable shores where the story of life could be quietly unfolding, waiting for the day we finally learn to listen. The profound silence from these 25 worlds whispers a haunting question. If the galaxy is so rich with potential homes, why have we encountered only emptiness? This is the heart of the Fermi paradox, the stark contradiction between the high probability of alien life and our complete lack of evidence for it. One compelling answer is the concept of a great filter, a hypothetical barrier so difficult to overcome that it prevents life from progressing to a detectable interstellar stage. This filter could lie in our past, perhaps the spontaneous genesis of life from non-living chemistry is an event of such staggering improbability that Earth is a solitary miracle. Or maybe the filter is ahead of us. The transition to a technological civilization capable of long-term survival might be the true bottleneck, a challenge that every species ultimately fails, succumbing to self-destruction or a catastrophe we cannot yet foresee. These 25 worlds, for all their promise, might be beautiful, empty cradles, their potential forever unfulfilled, or they could be living proof that the filter is behind us and that the cosmos is teeming with life waiting to be found. The only way to know is to look closer, to search for the definitive chemical traces of a living world. This is the monumental task of the next generation of observatories. The Habitable Worlds Observatory, a revolutionary space telescope now in advanced planning, will be our first dedicated tool for this search. Its mission is to directly image Earth-like planets and analyze the light passing through their atmospheres, looking for the subtle fingerprints of key gases. We will hunt for biosignatures, atmospheric imbalances that can only be plausibly explained by biological activity. The simultaneous presence of both oxygen and methane, for instance, is a powerful signal. These gases react quickly and destroy each other, so finding them together means something on the planet's surface must be constantly replenishing them, a process life excels at. Finding such a signature on a world like Lytton Star B or TRAPPIST-1e would not just confirm a habitable environment, it would suggest that the Great Filter might not be a universal death sentence. It would tell us that the transition from chemistry to biology is a path the universe treads more than once, and that the silence we hear may simply be the quiet of a cosmos where life is still learning to speak. This grand tour of 25 worlds reveals a cosmos richer and more varied than we ever dreamed. We have stood on the twilight line of a tidally locked planet, gazed up at multiple suns in a single sky, and dived into the abyssal depths of global oceans. Each of these alien shores, from the violent flares of Proxima Centauri to the serene calm of Lytton Star, tells a different story of what a habitable world can be. They are not mere copies of Earth, but unique masterpieces of planetary evolution, each with its own rules, its own challenges, and its own breathtaking beauty. This incredible diversity is the most powerful argument that we are not alone in the universe. The sheer number of possibilities, the countless ways a planet can cradle life, makes the existence of other living worlds not just a hope, but a statistical near certainty. The silence is not emptiness. It is a universe holding its breath. Now we want to hear from you. After this journey across the stars, which of these alien worlds would you most want to set foot on? Would you choose the deep red twilight of Kepler 1649c, or sail the endless seas of a Hycean world? Share your cosmic destination in the comments below, and subscribe to continue this adventure into the deepest mysteries of the cosmos.